Welcome, everyone. For today's prep, we're going to look at, or start to look at, how do we computationally find the intervals of concavity for a function? And we're going to do this using the second derivative. And then with this, we'll also see how to find the inflection points. The inflection points are where the concavity changes. Okay, so the main result here that we're going to use is that if we're looking at an interval from a to b, if our second derivative is greater than 0, then the original function is concave up. And if the second derivative is less than 0, well then our original function f is concave down on that interval. So again, it comes down to finding the interval of concave up and concave down comes down to a sign chart based on now the second derivative. So intervals of increase, decrease, that use the first derivative. Now for intervals of concave up, concave down, we're going to use the second derivative. So what this says is that if f double prime is positive, well then f is concave up on that interval. And again, concave up means it has this kind of shape. And if f double prime is negative, well, that implies that our original function f is concave down, and that has this kind of look. Okay. So, and just like we had critical numbers for the first derivative, well, we're going to have, important values for the second derivative, and we're going to call these inflection numbers. So, well, possible inflection numbers. So the number x equals c, we're going to say it's a possible inflection number if the second derivative is equal to 0 there, or the second derivative is undefined there. So just like with intervals of increase, decrease, we wanted to know when was the first derivative 0 and when was the first derivative undefined. Well, we're going to do the same thing now for the second derivative. And our strategy for finding the intervals of concave up, concave down is going to look exactly the same as finding the intervals of increase, decrease. The only difference here, and ooh, there's a typo. The only difference here is we're using the second derivative. So this should be second derivative. So it's all the same steps. Now we're just doing it with a different function, the second derivative. So calculate the second derivative, figure out where the second derivative is 0 and undefined, and then do a sign chart for that second derivative. So let's try an example. Let's look at example 2. And I just want to start with finding the intervals of concavity for this function. So we have this function 1/3 x cubed minus 2x squared plus 3x plus 1. So the first step is we got to figure out the second derivative. We got to get our second derivative here. So we'll call it f double prime, but before we get to f double prime, we need the first derivative. So let's get the first derivative, and then we'll get our second derivative. All right, so let's differentiate that first term. So derivative would be x squared. So we bring the 3 down, and it would cancel with the 1/3. So we just have x squared. Then over here, we bring the 2 down, multiply it with the negative 2, so we get minus 4x. And then finally here, differentiate that, we get plus 3. And then the derivative of 1 would be 0. Okay, so that's our first derivative. So now we need our second derivative. So we're going to do it again. So differentiate the x squared, we get 2x. Differentiate the minus 4x, we get minus 4. And then derivative of that plus 3 all by itself is just 0. Okay, so we got our second derivative. And usually, if there's more going on here, you want to try to factor it. But this is already pretty well factored. So we'll just make a note, factor if necessary. Not really necessary here, though. All right, so then we want to find the possible inflection numbers. Okay, so this is where the second derivative is either equal to 0 or where the second derivative is undefined. Okay, so those are the two options. And we've kind of mentioned this before, but usually the only way our second or our first derivative is going to be undefined is, the most common way, is if we have a fraction and we want to look for division by 0. We don't have any division here, so there is no division by 0. So that's really what you want to look for. Look for division by 0 for that derivative being undefined. So in this case, we don't have any division, so none. Okay. So instead, as usual, in most of the functions we're going to be looking at, the interesting stuff happens with this derivative being equal to 0. So we're going to take our second derivative, so the 2x minus 4, we're going to set that equal to 0, and then we just want to solve that equation for x. And this is an equation that we can just directly solve. So we can add 4 to both sides. So if we add 4 to the left, it would cancel those out, and then we'd have plus 4 on the right, and then divide both sides by 2. So we get x is equal to 4 over 2, or just 2. And so this, we're calling this a possible inflection number. Okay, so just like usual, but now we're doing it for the second derivative, the next step is to do a sign chart for f double prime. And looks like we're gonna move this up. All right, so we'll draw the x-axis, kind of like a regular sign chart here. So let's get our x-axis. We'll plot the possible inflection number that we found. So we found x equals 2, so let's plot that on our sign chart. And that was the only one that we found, so it splits the x-axis up into 2 intervals. So we have everything to the left, so from minus infinity to 2, and then we have everything on the right, 2 to infinity. And then we want to figure out what is the sign of f double prime, and then ultimately what is f doing on each of those intervals. And because there's only a single factor here for f double prime, we can just pick test numbers and just plug right into that second derivative. So we want a test number for this first interval. So just something less than 2. So we could pick 1, but 0 is always a good one if you can. So let's do 0. And when we plug that into our second derivative, what do we get? Well, we're going to get 2 times 0, so we're going to get a 0 there, and then minus 4. So we get minus 4. So that means our second derivative is negative on that first interval, which means our function f is concave down there. The original function f is concave down there. Okay, well then let's go to the next interval. So we want something bigger than 2. So pick a test number, make it easy. So maybe 3. We're going to plug that into our second derivative, see what we get. So again, if we go up, we're going up right to here. We're plugging 3 in. And when we do that, we're going to get 2 times 3, which is 6. So we get 6 minus 4 is positive 2. So we don't really care about the number. We just care if it's positive or negative. So we get positive over here. And so when our second derivative is positive, that tells us that our function, the original function, is concave up. Okay. So what we're going to look at in class is what's happening here at x equals 2. This x equals 2 is kind of a special point. And we're going to call that an inflection point because there, well, I guess we'll look at it now. We're doing it now. So an inflection point or an inflection number is an x value. It happens at an x value that satisfies those two, one of those two conditions. But we also see F double prime switches signs there. So what we have is that in this example, our second derivative switches signs at x equals 2. So that's why we're calling this a possible inflection number, because we don't know if this is an actual inflection number at this step yet. We need our sign chart to kind of make that determination. Okay, so let's write out what we found. For this function, let's go back up. So to answer it, we found that this function was concave up on the interval 2 to infinity. We found that it was concave down on the interval minus infinity to 2. And we found that there was an inflection point at x equals 2. So those are the three things that we found. And we'll look at inflection points more in class. So we'll come back to this. But what we're really looking there for is it's one of these values that we found from before, one of these x values. And then we just want to look on our sign chart to see if we actually do change concavity. So what we do see here, right in the middle, is we do see a change in concavity. That's really what we're looking for. So because we go from concave down to concave up, or if it was the opposite, if we went from concave up to concave down, that would also make that an inflection point. So we just want to see kind of some change in shape. So if we see a change in shape at that x value that we find, well, that's what makes it an inflection point. Okay, so we'll definitely do some more examples of those in class. So we'll see you then. Bye-bye.